Hey everyone, welcome to another episode of the ZK Whiteboard series. I'm Brendan, I work at Polygon, and I'm here with Mary Maller. Mary's a leading Snark researcher responsible for works like Sonic, Marlin, Caulk, SnarkPack, and she's currently at the Ethereum Foundation. Welcome, Mary.
Thank you for the introduction. So today I'm going to be talking about lookup arguments, which are a key technique in the Snark world to try and make provers faster.
We like that.
So with a lookup argument, you would have some value W, which is secret. You're trying to keep it hidden, but equally you do want some kind of constraint on W. You want that it's included in some kind of set. So, and this set would be public. So for example, it might be 0, 3, 4, 7, trying to come up with a set that doesn't have any particular structure here. So a lookup argument would allow you to prove that W is inside this public set, but it wouldn't reveal any other information about W.
Cool. So where might we use a lookup argument?
So a classic place where we use them all the time is actually in our Snark constraint systems, because often it is quicker to check that W is in some pre-computed list than to check all of the constraints on W that would lead to W being in that pre-computed list. Mm-hmm. Lookup arguments are also very, very related to lots of other concepts in the literature. So there's a lot of overlap with set membership proofs. There's a lot of overlap with accumulators, with vector commitments. No doubt there's some that I've forgotten. But in the context of sort of trying to make Snark circuits faster, typically we would call them lookup arguments. So my plan for today is first to just run through an example of how you would represent a range proof in a constraint system. And this is just to sort of try and get you familiar with how we would actually program these things, I guess. Mm-hmm. After that, I'm going to be talking more about what a lookup proof is, what is the motivation behind them, that sort of thing. Then I'm going to move on to talking about vector commitments and how you might represent them in the standard basis, how you might represent them in the Lagrange basis. These are very relevant to lookup arguments. Then I'm going to talk through the Halo 2 lookup argument, and I'll be finished by presenting some of our new work, which is in the Caulk lookup argument.
Sounds great.
Okay. So for a range proof, again, we have a witness W, and we're trying to prove that it's in the set 0, 1. I'm not going to write it all out. 0 through, let's say, 8, which is equal to 2 to the 3. And again, W is private. We don't want to reveal W. This is a simplified example. Typically, when you would be proving these range proofs, 8 would be something more like 64. But for this example, I'm writing out on the board, so I'm trying to keep it simple. Range proofs like this appear all of the time in Snark circuits. They're absolutely everywhere. And the reason is because we're working over a prime field P. Mm-hmm. And this means you get something called overflow errors.
Which can be really bad for cryptocurrencies, right?
Oh yes, they can be bad. So what I sort of mean by this is that if you have inverses basically. So if you have the number 4, then it is certainly the case that P minus 4 exists. Mm-hmm. So what you would do with a range proof is you would say that W is not in fact equal to P minus 4 because it's out of range.
So, but not to belabor the point, if we weren't checking this, then there are situations where I could mint like P minus 4 coins, which would be pretty bad.
You know, 2 to the 256 minus 4 coins. That's a lot of coins.
I could retire on that.
One of the classic ways in which we would try and show that W is within this range would be through doing a binary decomposition. So we would say that there exists values B0, B1, B2, all included in 0 and 1, such that W is equal to B0 plus 2 times B1 plus 4 times B2.
So we're sort of splitting it into bits where the BIs are bits and we can express anything in this range in that form. That's where.
Exactly that,
Okay.
yes.
Cool.
These B values, they're also private though, because revealing B0, B1, B2 reveals W directly. Cool. So you also have to keep those hidden. And this means you get some amount of witness blow up, because before where you had a witness of size 1 element, you now have a witness of size 4. Mm-hmm. And this obviously blows up more with larger ranges.
Okay, cool.
We also need some additional constraints here, because I've said that B0 and B1, B2, they're in 0 and 1, but you do have to check that. So the way that you would check that is you would check that 0 is equal to B0 times B0 minus B0. The only way you can satisfy this equation is if B0 is 0 or 1. And you do the same for each of your other bits.
So guaranteed to be bits.
This guarantees them to be bits.
Cool.
But as you can see, this is also blowing up our number of constraints in our circuit, because we now have one additional multiplication constraint per bit. And actually, if you're in systems, universal snarks, where addition costs are no longer free, there's also some addition constraints going on here.
So what does this look like in terms of like an R1CS matrix?
If we were to put this in terms of an R1CS matrix, which is a constraint system which is used a lot in the snark world, I think more recently a lot of people have been moving to the Planck arithmetization scheme. But for this example, I'm going to explain it in terms of R1CS. Sorry. So R1CS really works in terms of matrices. It's like a vector and matrix type of argument. So you have one matrix times by a vector. Sorry. One matrix multiplied by your witness vector. Times by another matrix multiplied by your same witness vector. It'd help if I could keep my witness vector the same. Let me separate this. Minus a third vector times by your witness vector. So your witness vector appears 3 times. And you're trying to show that this is all equal to the 0 vector. And you want it to be the case that we can find a matrix here, here, and here that represents the constraint systems over on that side. So how do we actually do this? Well, our first constraint, we don't have any multiplication gates here. So we're going to look straight to this matrix. And we see here that we have W equal to B0 plus 2B2 plus 4B2 plus 2B1. So this can also be seen as out. 0 equals minus w plus. So in order to represent that constraint, I'm going to have 1 times w plus, minus 1 times b0 minus 2 times b1 minus 4 times b2. And I want that to equal 0. There is nothing happening with the multiplication constraints. So up here, we just have 0, 0, 0, 0, and 0, 0, 0, 0. Our next constraint, we have to actually enforce a binary constraint on b0. And this is a multiplication constraint. So we're going to be working up here. And really what we need to do is we just need to select out the b0 from each of these matrices. So that would just be 0, 1, 0, 0 here, and the same here, 0, 1, 0, 0. And then we need to minus it off, so 0, 1, 0, 0 on the bottom matrix. The other binary constraints are all of the same, so we do the same thing. 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, and 0, 0, 0, 1. And there you have it. This would be an R1CA way of trying to represent that W is between 0 and 8.
Cool. Yeah, because we're enforcing that W can be decomposed into these BIs, and then that the BIs are all bits. And
yes.
Yeah, cool. Oh, awesome. Thanks, Mary.
Okay, so as you can see here, we have that the witness has been like a bit blown up because of how we're having to represent these binary constraints such that the snark can read it. I'm just going to now try and explain that in a more visual way and provide a schematic. And grab what's up here first. So suppose you have some computation that you're trying to prove. So I'm going to call this computation as a function f. F is going to take as input a public value x. Is it okay if I erase up here, do you think?
Yeah.
It's also going to take as input a private value w. The computation will output y. And then what your snark prover would be doing is it would be saying, I know w such that f of x w equals y. And really what you'd often like this to be in like real life, I would say, is like maybe a C program or a Rust program, like an actual computation. However, we do actually need this to be something that the prover can read. We need to be able to snarkify it. And this means that we have to arithmetize our function. And the arithmetization process is where a lot of the prover costs come in for snarks.
Because we can't just use a lot of the operations that we have access to, like in a Rust program, like there's no less than or greater than operator or any of these, like anything except for addition and multiplication, right?
Yes, there's lots of things that you don't have access to. You also, if you wanted to have an if loop, you would have to iterate both possibilities are in your if loop really and sort of say it's one of these two. It's hard to jump around in the program execution trace. There's lots of places where in order to arithmetize, you have to do things in a different way. So in doing so, much like we saw in our binary constraint example, you're going to blow up the size of your witness. So I'm going to write a bigger W in order to represent this. Again, a private value.
And so this is what we saw earlier, where we started with W and we ended up with a bunch of bits.
Yes.
Okay.
The thing with the bunch of bits as well is you might be there like, it's only a bit, it's only 0, 1, it doesn't actually take that much storage. In the snark world, that isn't true. Your bits cost the same as any other element in the field. So it really does hurt. And then we're going to have our function, which I'm now going to call big F. It's again going to take in a public value. And actually, the public value is the one thing which doesn't change much. This. Because the verifier knows this. And we still want to know that the output of this function, which should be the same function, just represented in a different way, is equal to y. Oh. So I know big W such that f of x, big W is equal to y. And yes, these two statements here should be equivalent if you've done your arithmetizing correctly.
So what does this do to like prover time or kind of the things that we care about in practice around snarks?
It explodes the prover time.
Okay.
Like not just a little bit either, we're talking orders of magnitude. Proving this, it was, the witness is often like many, many more times the size of this witness.
Okay. So if we're doing a bunch of range checks, then we might be in a tough spot because, from an efficiency perspective.
I mean, it's not undoable. It's not like this can't be done because it is done. It's just, it is an area where the quicker we can get this, the better we can get this arithmetization process, the faster our snark is going to be. It's one of like the key places to tackle. It doesn't, however, affect proof size, really, and it doesn't affect verifier time. This is purely for the prover time.
Cool. So hopefully there's a better way for handling range checks, and so like something that maybe will have like a smaller blow-up factor for our arithmetized circuit.
Yes, there are definitely better ways, and one of the sort of really promising ways which has come out is to use lookup arguments. No surprises there, I'm sure. Shall we rub this out?
Sure. So Mary, what's a lookup argument?
So before I sort of said that we want to prove that we have a private W, which is included in some set 0 through 8. This set is public. So what we can do is we can pre-commit to it. We can set up a table with all of the values between 0 and 8. So we generate a table. And in the table, we have 0, 1, 2, 3, 4, 5, 6, 7, a very even table.
And we can do this because we know that no matter what W is, we'll always have to check that it's between 0 and 8. And so this is not something that depends on the witness. It's something that we can kind of bake into our circuit.
Actually, I think it is something which would depend not so much on the witness, but on the circuit. Like if you're using these lookup tables, I'm giving them in the specific case of range checks because they're one of the cases that come up all of the time. Mm-hmm. But really what you'd probably want to be looking at is more what kind of operations in your specific circuit come up all the time. Like if you were trying to prove a hash function, then one of the things that you might want to store in your table is the possible outputs of the S boxes.
Yeah. Oh, I just meant that like it's something that we can pre-compute once and sort of like bake into our constraints that we
Yes.
wrote, and then okay, cool.
Yes, no, you absolutely can do that. So yes, then we've got our table. I'm going to call this is equal to T. And we just want to find a way of proving that W is included in T.
And hopefully with fewer constraints than our previous binary decomposition.
And hopefully in a way which is more efficient than doing the full binary decomposition.
Cool.
Okay, so we have a table that we need to pre-commit to. So the next thing I'm going to be talking about is different ways in which we might commit to this table.
Cool.
Mind if I come over here?
Yeah.
So if we're sort of thinking in polynomial notation, which is something which certainly the zero knowledge world in general, I'd say, is moving towards more and more and more, we would say that we have a polynomial, f of x, and we might want to commit to a set of values in a table, a0, a1, let's just say a2, keep life easy, by having them as being the coefficients of the polynomial. a0 plus a1 x plus a2 x squared. I would say that this basis is very good for some settings, but actually often in the settings that we're working in, it's not necessarily the best way. And the reason is because it's just a little bit more complicated to open, right? So if, for example, you wanted to open A1, the easiest way to do this would be to provide another polynomial, let's say G0 of x and G1 of x, and then you would want to prove that f of x minus a1 of x is equal to G0 of x plus G1 of x times by x squared, and that G0 of x has maximum degree 0. So this would give you that a1 is indeed the coefficient relating to x for f of x, because this term cannot have an x to the power 1 term. But as you can see, it's quite convoluted. Like we've got degree checks, we have multiple polynomials, there's sort of quite a few steps to doing this. And there is an alternative basis called the Lagrange basis, where you don't have to do this.
Sounds good.
Oh, I should actually keep this bit, but do keep going.
Would you like the f of x or?
Yeah, but just the f of x, these can go. So a way that you can do this instead is you can say that f of x is equal to a0 L0 of x plus a1 L1 of x, thank you, plus a2 L2 of x, where L0, L1, L2 are the Lagrange polynomials over the set V is equal to omega 0, omega 1, omega 2. I know these look like W's. I will avoid using W's for this section of the talk because they look so much like W's. They're actually omegas. They have nothing to do with the witness. They're completely public. They're usually roots of unity, actually.
Take me back to abstract algebra. What's a root of unity?
Root of unity. So this is a set of size, not a power of 2, which is not helpful. It would always be a set of size, a power of 2. But a root of unity would be a value such that wi to the power of n is equal to 1 modulo whichever field you're working over.
And so we call that an nth root of unity.
That would be an nth root of unity.
Okay.
I can't make this a power of 2, but pretend.
Okay, cool.
Probably you might want me to explain what a Lagrange polynomial is.
Yeah, that'd be good.
Cool.
Should we erase, maybe save this and erase? So.
I think erase that.
Okay.
And actually, I might need to erase both to make space. I'll try and rewrite out some of the fact that we have that set V, because V is going to be important. Sneak over here again. V is equal to the set omega 0, omega 1, omega 2. And we have that L0 of x is the unique polynomial. There's only one of them. Polynomial. Unique poly. Such that L0 of omega 0 is equal to 1, L0 of omega 1 is equal to 0, and L0 of omega 2 is equal to 0.
And so the others are kind of defined similarly, where if the indexes match, it's 1, and if they don't, it's 0.
Yes, exactly that.
Okay.
And these polynomials, they have like a very specific formula as well. Okay. Like they're fairly easy to compute. We have L0 of x is equal to the product between I equals 0 and 2, I not equal to 0. So actually I equals 1 to 2, but for the others I'm going to write it like that.
Sure.
Of x minus omega I, all divided by the product I equals 0 to 2, I not equal to 0 of omega 0 minus omega I. Thank you. So yeah, you can see here, if you were to insert omega 0, you would get 1 because it divides exactly. If you were to insert omega 1, then you have omega 1 minus omega 1 in your product, so that would go to 0. One thing also worth mentioning is that when these are roots of unity, These polynomials are very quick to compute because we have fast Fourier transforms. But I'm not going to go into any more detail other than saying their existence here.
Okay, cool. So how does the Lagrange basis sort of save us when we have to open our vector commitments?
Well, again, we've got our public set V, which I've conveniently rubbed out. If you want to be able to open F at A1, you would just need to prove that F of omega 1 is equal to A1.
Seems very convenient.
It is very convenient. And yeah, this check is very easy to do. In particular, one way that you would do it when you're using KCG polynomial commitments is you would prove that f of x minus a1 is equal to x minus omega 1 times some quotient, not vanishing, quotient, polynomial q of x.
Cool.
So yes, when we're committing to tables, this is how we would do it.
So we just, so right now we have a table with 3 elements and we instantiate a polynomial of this form.
Yes.
Cool. And then when we want to open, depending on our polynomial commitment scheme, it can look a little bit differently. You can only do this if
you've got pairings.
Yeah,
it's true.
yeah, exactly.
So specifically, if you were doing Halo 2, you wouldn't do it exactly like this.
Yeah, yeah. Cool.
So I would say keep this up here, but
Okay.
I'll keep that one as well.
Okay.
So I'm now going to talk about how this kind of polynomial would actually be used in the Halo 2 lookup argument. Actually, the idea to use lookup arguments wasn't originally Halo 2. It was originally a Planck idea, the lookup argument. And this is like a really, really good paper, really sort of revolutionized how people do things. But Halo 2 is quite a lot simpler. So for the sake of a whiteboard session, I thought it would be a better one to explain. So again, you have a table of values, such as the one above. But you also have another polynomial, also over a Lagrange basis, which is your polynomial committing to your witness. So this one's called f of x. I'm going to call this a of x. This may not be at all consistent with how the Halo 2 people are doing it in terms of their notation, so sorry about that. And a of x is going to be equal to, let's say, b0, L0 of x.
So these BIs, are they like elements from our witness or like things that we're trying to look up?
These are elements from our witness. And actually, a lot of the time they're going to be not values in your table because you're not interested in doing a lookup argument for this value. And the way they handle that is via selector polynomials, which I'm also not going to cover. Mm-hmm. So for simplicity, just assume that every witness element in your computation is something which you want to be equal to either A0 or A1 or A2. So one of the sort of first problems that you're going to come across here is that these values, B0, B1, B2, should say B0, B1, B2, you all want to be included in A0, A1, A2. These are not necessarily going to be in the most convenient order.
Like B0 could be A2 and B1 could be A0. And...
Exactly that.
Okay.
I might even use a red pen for the first time in order to put that idea out there. Like maybe you have this
You guys-
kind of structure.
It sure would be nice
Or-
if they were, because then it would be the same polynomial.
Yeah, if they were exactly
Easy
equal.
check.
You might even have repeats, actually. That's a
Yep.
good point.
Yep.
So you might have that both B0 and B2 are equal to A2. And this is an additional challenge which you have to work with.
Okay.
So the very first thing that Halo 2 is actually going to do is it's going to permute these values such that they're in a more convenient order.
Okay.
So we would want to have some alternative polynomial. Let's call it a dash of x, which is equal to, what do we want? Probably want B1 first, which is equal to B1 L0 of x plus B0 L1 of x plus B2 L2 of x. But the prover might not give you the correct value of a prime of x. You sort of really need to enforce that that a prime is genuinely a permutation. You don't care what permutation, but you care that it's a permutation. So the very, very first thing they do is just a permutation argument. Just to say a prime of x is equal to some permutation of a of x. I probably need to make a bit of space again. We'll keep the a prime of x.
And would you like to keep this? Or?
Yeah, for now.
Okay.
So we got a prime of x. We've already proven that it's a permutation of a of x.
And for now, for the purpose of this session, we're just treating the permutation argument as a black box. And
Yeah.
Okay.
And now we have a much, much nicer structure. We have that B0 is now mapping to A1. B1 is mapping to A2, and B2 is mapping to A2. Mm-hmm. Probably made life a bit difficult for myself by not having B0 starting at A0, actually. So I'm actually going to just change this and make life easy.
Sure.
Pretend I wrote it out the easy way first time. One quick note I will add is the way they get around the thing where they're like, I've made it difficult. This B0 doesn't map to A0. The way they get around that is they actually permute f of x as well. So they permute f of x to be in a convenient order as well as a of x to be in a convenient order.
Okay.
Okay. And now our problem becomes much simpler. We simply have to prove two things. We prove that either a prime of omega 0, actually, the either constraint isn't relevant yet, that will come. We prove that a prime of omega 0 is equal to f of omega 0. That's just like our starting point.
Okay.
We then prove that either a1 prime of omega 1 is equal to a prime of omega 0, or a prime of omega 1 is equal to f of omega 1.
And we can see like the omega 0 is picking out this value and this value to start, and so we're just iterating through.
Yes.
Yeah, and so
And we will do this with omega 2 as well.
Okay.
I'm not going to write that out again, but
Sure,
just
sure.
for every value you prove that is either equal to the last value in a prime, or it's equal to the value relating to f of x.
Okay. And because we've permuted a prime and theoretically f, if we needed to, we know that we're basically like picking out all of the
Yes.
values. Yeah.
The one sort of way in which this is really nice is that you're just working with permutation arguments. Everything is fairly simple. And usually what they're going to do is they're going to make it so that the size of the table corresponds very conveniently with the size of the witness.
Mm-hmm. Nice.
But if you do have it the case that you have like a very, very large table, you're always going to have it the case that this lookup argument is linear in the size of the table, because you have to do the permutation argument.
Mm-hmm. And so, yeah, so like when we use lookups, we sort of have to strategically pick a table size that is kind of optimal. Like we might use 16, a table size of 16 or some smaller value, so that we don't have to like pay the full cost of the
Yes.
table. Yep. Cool.
So I've sort of explained how the Halo 2 argument is working from like a very, very high level. With Caulk, we were trying to do something very different, in the sense we're still trying to do a lookup argument, of course, but we're trying to beat that sort of linear time restriction. We wanted it to be sublinear in the size of the table.
Which is nice if we have bigger tables, right?
If you have very big tables.
Very big tables.
Then
Okay.
yeah, but it becomes pretty nice.
Okay.
Yeah, we can rub this off. And actually, I'm also going to rub off f of x, because I want f of x to have a few more terms in order to be a bigger polynomial.
Okay.
I might need to write a little bit smaller for it to fit. So let's say that f of x is equal to a0, l0. How many do you reckon I should go up to?
We can always just use like an I index.
Let's do that. Okay, is equal to the sum of I equals 0 to n minus 1 of ai li of x for bigger. It's still not like big in cryptography terms. It's still like, I would say that probably we can go up to 2 to the 28
Which is still quite a bit bigger than is like basically reasonable with the Halo 2 style arguments or lookup, right?
Yes, it works for like a lot of use cases.
Yeah.
So this is now going to be our table. And kind of the key trick in Caulk, I would say, is that we still want to be working over sets of roots of unity. And for sure, f is defined over v, which equals omega I for I equals 0 to n minus 1. But our idea is that when we have our polynomial a of x, I think the notation we use in the paper is phi, so I'm going to do that here. Phi of x is equal to the sum of bi. We're still going to have it over a Lagrange basis, but our Lagrange basis, this is the, give me a letter.
I guess, W or
All right.
T? Using T for a table.
W is going to be over, say, mu I equals 0 to not n minus 1.
So what is mu?
M minus 1. Mu is a different set of roots of unity.
Okay.
W is going to be much smaller than V
Okay. Okay.
in this case. So then we can have phi of x is equal to V0 times a different set of roots of unity that we were using L. Am I going to use M? Doesn't really imply Lagrange. I'll use lambda. Lambda I of x. And we still want to prove that every BI is equal to AJ for some J. But the thing here is that we're not going to have perfectly that lambda I and Li are the same set, and equally V and W are going to be different sets.
So just for my understanding, is the lambda, are those Lagrange polynomials over the set of mu's, or? Okay,
Yes.
okay.
So really what we're doing here is we're getting a different trade-off. We are going to have costs which are going to depend on this M, so the size of our commitment, but they're not going to depend on the size of our table.
Cool. So, and because M is smaller, much smaller than N.
In some cases.
Yeah, okay.
If you have a case where M is much larger than N, then actually currently we have quadratic costs, so you really would not want to use Caulk there.
Okay,
But if M is small, then it works quite nicely.
Okay, nice.
Okay, so now we want to relate phi of x to f of x. But our problem is that the roots of unity are different. Mm-hmm. So what we're going to do instead is we're going to have some polynomial u of x, which is going to select out the roots of unity from f of x, which are like of interest to us, right? So our u of x is going to equal the sum of some omega ij, I'll call it, in order to indicate that it's not going to sum over all of the omegas, only the ones that are interesting.
And so by interesting, is that just the set that actually we're matching on? Or,
Yes.
Okay. Yeah.
That's just the set that we're matching on. And then what we want to do is we want to prove that the omega ij's are roots of unity. And we also want to prove that for every mu j, we have that f of u of mu j is going to be equal to phi of mu j.
And so we have to prove this because there's no way in the circuit, like without another lookup table, that we could like guarantee that these values that we're providing are actually like part of the set of omegas.
Exactly that, yes.
Yeah. Okay.
But proving that a value is like a root of unity is kind of like very doable because of what a root of unity is, right? Like remember that we have that omega ij to the n is equal to 1. This is a very checkable relation. Mm-hmm. You can check this in log n time, to be precise. In log n time, just by using the square and multiply algorithm inside your constraint system. Mm-hmm. And that's exactly what we do.
Cool.
So I probably could go into more detail, but equally I think I won't. I will just sort of finish by saying that the overall complexity we get in terms of prover time here is on the order m squared plus m log n. We're very keen to get rid of this m squared term. We sort of intuitively think that it should be possible, but we've not figured out how to do it. So this is sort of something which I would say, like, if you have an idea, it's worth exploring.
Cool. And so right now, I think that my understanding is the scheme depends on some, like, on using pairings for like some linearity tricks.
Yes.
Is there, like, can you imagine a way where you wouldn't, you could remove the pairing requirement, or is that?
It would be very challenging, actually, just because, like, the way that we're making this check fast is by using the KCG commitment scheme. We sort of say we've got this pre-computed KCG commitment, which shows that F opens at this point to that point, and then we just like prove knowledge of our KCG opening.
Yeah.
If you wanted to do the same in a discrete logarithm setting, you end up working with a proving system which has random oracles all over the place.
Yeah.
And these are much harder to integrate in a sort of pretty way into your proving system.
Yeah.
So again, I don't think it's like impossible, but there are additional challenges that you would face.
Cool. So is there anything that's kind of on the roadmap for either Caulk or lookup tables that that you're working on, or is this sort of?
I mean, I would say that we are sort of exploring, can we get rid of the m squared, but we've not solved it. So I don't want to get your hopes up there.
Cool. Well, so I guess to recap, we looked at certain things that are expensive and very common in circuits, and like range checks, and how we might use techniques like lookup arguments to make them less expensive. And then we looked at the Halo 2 lookup argument, and then Caulk.
Yes.
Yeah, this was really great. Thanks to Mary, thanks to the ZK Hack team, and to everyone for watching.
Thank you.